Hi everyone, welcome back once again. Today we are going to look at the application of calculus, and that is your optimization and rate of change. All right. Okay, application of calculus. All right. So far we've been learning about calculus. We've been learning how to derive, how to use first principle, finding the derivative, sketching a cubic graph, finding the point of inflection, finding the mark turning points, and all those other stationary points, right? X-intercept and all that. And we've been learning all those things in calculus, but now it's also very important that we also look at some of the real world application of calculus. How can we apply calculus in our real world? And this is quite an easy topic, although most of you guys might say, oh, application of calculus is challenging, but I'm telling you, it's quite an interesting, very practical topic to learn, because now we are applying calculus, right? So basically, how do we do this? Let me give you a scenario. Probably if you go to a shop and you buy a wire fence, right? A wire fence, something like that. Then maybe you buy a 20-meter wire fence, and you want to determine, Ori, what is the maximum area that it can cover, right? You want to know, oh, actually, what is the maximum area that this thing will cover? So you can actually use the knowledge of application of calculus, optimization, which is maximization and minimization, in order to determine the maximum area it can cover, right? So also for in another case, maybe you want to build a rectangular swimming pool, right? And you want to determine the maximum volume of water that can occupy that rectangular swimming pool. We can use the idea of what? Of maximization and minimization, which is a topic under the application of what? Of calculus. So basically in this lesson, we're just going to be looking at that and learning how we can actually maximize things, right? We learn how to maximize, or rather find the maximum or minimum area or volume, right? As well as we minimize variables such as cost. Maybe you want to find the minimum cost, right? So perimeter and so forth. So that's the topic we just are interested in looking at in this session, right? Okay, let's now quickly look at the rules for doing this, the rules for maximization, the rules for minimizing all these values, right? So very, very important. In order to maximize or minimize an object, what you have to first do, you must first determine an algebraical equation, right? In terms of only a single variable. Very, very important. Step number one, you must able to determine an equation in terms of a single variable. Then after that, what do? You find the derivative of that equation. And why are we finding the derivative? It's because we know that from the derivative, it's actually easily calculated. We know that at the maximum value, or at the minimum value, the first derivative is equals to what? Is equals to 0. So we can use this idea to say, actually, to maximize, I can actually find the derivative and equate it to 0 and solve for that variable and see which one will maximize, which one will minimize, because the first derivative, it's actually the turning point where is equals to 0. So using that knowledge, get your first derivative equated to 0 and solve for the variable that they are looking for in order to yield your maximum or minimum values for that given object. All right, I know now you might be, this lesson is quite confusing now, but let's just quickly look at an example and see how this goes. All right, so let's look at our first example. We're given that a cylinder is enclosed at both ends, and it is to have a volume of 2000 pi cubic centimeter. What should its dimension be if its surface area is to be as small as possible? All right, so obviously in this question they want you to get the dimension, that is to calculate the value of R and H that will enable the surface area of this cylinder to be small as possible, that is to be minimized, right? Minimum. Okay, so this is actually application of calculus. How do we approach this question? The first step you do is to create an equation for this problem, right? So your equation, you should create an equation that you'll be able to derivate, right? But in this case now, you must be very careful. You create an equation for something that you want to minimize. So in this case, we're going to create an equation for what? For surface area, right? But now, because they want to make the surface area small as possible, so we know that the surface area of a cylinder is 2 pi r squared plus 2 pi rh, right? So now the problem is we can't find the derivative of that equation because it has different variable. It has r, it has h, right? So the second step is to ensure that your equation that you want to minimize, that you want to derivate, must be having the same variables, right? So in the question, they will obviously give you something that will enable you to express those variables in terms of one another. So in this case, we are given the what? The volume, right? So we can use this volume and actually go and express one variable in terms of the other, so that we can go back to our equation that we need to minimize then and solve for those dimension. All right, so we know that the volume is equals to area of base. Base is a circle, right? So which is pi r squared multiplied by what? By height, right? What is the volume? We are given that the volume is 2000 pi is equals to pi r squared multiplied by height. So we can actually make height the subject of the formula by dividing by pi r squared, dividing by pi r squared. Pi and pi will cancel, and our height will be equals to what? 2000 over what? Over r squared. Can you see? So using the information we are given, we're able to express one variable in terms of the other. So now we can actually make our equation to have the same variables, right? Then we derivate. Okay, so our surface area, I can just use area rather than writing SA, right? Let me just say area, right? But we know it's surface area. So it's 2 pi r squared plus 2 pi r. So where there is height, I'm going to replace it by what? By 2000 over what? Over r squared. So r and r will cancel there, and our area is going to be 2 pi r squared plus 2 pi multiplied by 2000. 2 pi multiplied by 2000, it's actually going to give us what? 4000 pi, right? 4000 pi divided by what? Divided by 1 r there, right? R exponent 1. So now we have managed to express our surface area that we need to minimize in terms of one variable, right? We can just write this equation properly such that we can be able to derive. So this is r exponent 1. If I take it on top, it will change to be r exponent what? Minus 1. So I can write it as r exponent minus 1 there. Okay, so now we have written our area that we need to minimize, make it small as possible in terms of one variable. The next step really is for you to just get the derivative, equate it to 0, and then calculate those variables. Okay, so meaning we're gonna get the derivative of the area. So it's gonna be 2 times 2, which is 4 pi, right? On the exponent we subtract 1, so we'll be left with r. We come here to this one, minus 1 times 4000 pi, it will be minus 4000 pi. On the exponent we just subtract 1, so minus 1 is going to be minus 2. Okay, so we equate our first derivative to 0 and go and solve for r. So I can just simply take a common factor for pi r there. It's going to be 1 minus what? 1 minus 1000 r exponent minus 3. Okay, when we take out the common factor 4 pi r. So 4 pi r will be equated to 0, and our r there will be what? Will be equals to 0, or we can 1 minus 1000 r exponent minus 3 will be equals to what? Will be equals to 0, right? So now it's just a matter of going to solve for r that side. So r exponent minus 3 will actually be equals to 1 over 1000. So when we take 1 to the other side and divide by 1000 both sides, so it's going to be r exponent minus 3 is equals to 1 over 1000. So to solve for r, we can apply the exponent of minus 1 over 3, so that minus 3 and minus 3 cancel out each other. Okay, so we're going to take it to the exponent minus 1 over 3. Then r will be equals to 1 over 1000 to the exponent of minus 1 over 3. Okay, to the exponent of minus 1 over 3 on your calculator is going to give us what? Is going to give us 10. Okay, so between r equals to 0 and r equals to 10, which one can make this surface area to be small as possible? Because now we got two answers. Obviously, r equals to 0, we can't really say it's a dimension because 0 stands for nothing, right? Meaning the correct answer will be r equals to what? R equals to 10. Now, they want the dimension. They don't only want r, they want all the dimension r and h that will make the surface area to be small as possible. So to solve for h, remember we had an equation from the volume. So h is equals to 2000 over r squared. So we're just going to replace our r by what? By 10. So it's going to be 10 squared. H is equals to 2000 over 10 squared, which is going to give us an h, which is equals to what? Which is equals to 20. So these are measured in centimeter. So our r will be equals to what? Let me just use a different color for this. So r will be equals to 10 centimeter, and our h must be equals to 20 centimeter in order to give us an area that is small as possible. Those must be the dimension. Okay, let me just repeat what we did here. When you are solving optimization problems, what you do is you have to create an equation, right? But you don't just create an equation, you create an equation for something that you want to minimize, you want to maximize. So in this case, we wanted to minimize the surface area, hence we had to write the equation for surface area. Then the next step is to derive that equation. But before deriving an equation, you must make sure that the variables are the same. So obviously in the equation, they will give you something that will help you to ensure that you express one variable in terms of the other, go and replace, get the derivative, equate it to 0, and solve for those things that they need. Okay, so let's just look at a different example in order to help you conceptualize this. Example number 2, it says a rectangular area is to be enclosed on the 3 sides, right? Only on the 3 sides by a fence and an existing hedge, which forms the 4th side, right? You have a hedge this side, you can see the hedge, then but what we need to do is we need to enclose it on the other 3 sides by a fence, x, y, x. Okay, it says find the maximum area of the rectangular area, right? And its dimensions if 100 meters of fencing is available. Okay, so they have a total meters of fence that is 100, right? So they want to know the maximum area that that 100 meter of fencing can actually cover, right? So now we need to use this ideology of what? Of maximization and minimization, and this is actually application of calculus. So the first step, what you do, you create an equation, right? For what? For something that you want to maximize or minimize. So in this case, we want to maximize the area, right? So we are going to write area. What is the area of a rectangle? Area of a rectangle says length times breadth, right? Length times breadth. Our length is what? Is y. Our breadth is what? Is x, right? So or yx or xy. So that is our area. But you'll notice that the next step says we need to derive, right, in order to solve for one of these dimensions. But look at this. We cannot derive if we have 2 different variables in the equation. So we must make sure that what? Our equation only contains only one variable, so that we can be able to find the derivative and actually solve this problem, right? So they will give you something that will help you to be able to express these variables in terms of another, right? So in this case, they give us what? The total dimension of what? 100 meters of fencing is available. So meaning that when you take your x plus y plus x, which is the total dimension of this fencing, it must be equals to what? It must be equals to what? 100, right? And actually we call this a perimeter, right? The dimension of 100 meters of fencing is available. So the perimeter of this portion that we need to fence is equals to 100, meaning x plus y plus x is equals to 100. We can express one variable in terms of the other, right? So because this will be 2x plus y is equals to what? 100. We can simply solve for y. Y will be 100 minus what? Minus 2x. Okay, so y equals to 100 minus 2x. We can go back on our equation for area and actually write it in terms of one variable. So where there is y, we're going to replace by 100 minus 2x. This is also being multiplied by x, right? So x will multiply 100, x will multiply 2x. So this will be equals to what? 100x. Our area will be 100x minus 2x squared. All right, so look at this. Our area now is expressed in terms of one variable. In order to maximize it, we can go and what? And differentiate it and get the derivative now, right? Okay, from there we got there, we are going to get the derivative now because it's expressed in terms of x. It's in one variable. So the derivative of 100x is going to be what? It's going to be 100 times 1, x exponent 1 minus 1, x exponent 0 is the same as x exponent is the same as 1. So 100 times 1 will remain 100. Minus 2 times 2, it's going to be minus 4. On the exponent, we subtract 1. 2 minus 1 will be left with 1, right? So we let our first derivative to be equals to 0 and actually go and solve for what? And solve for x. Okay, so 4x will be equals to 100. Then we divide by 4 both sides. Our x will be equals to what? 100 divided by 4, which is what? Which is 25. All right, so we got one dimension. Our x is equals to 25. Remember the question said we must get the maximum area and the dimensions, right? We got one dimension. X is equals to 25, and that is the dimension there, 25 units. Okay, so let's go and get y. To get y, we just simply go back to that equation and replace x and so for y. So y will be equals to what? 100 minus 2 into 25, right? So y is equals to 100 minus 2 into 25. Then it's going to give us what? 50 units. All right, so y will be equals to 50. So now we can get the maximum area of this rectangle, right? The maximum area, let me just use different color. Let me just write it on top. Maximum area is equals to length times breadth, which is x times y. So it's gonna be 25 times 50. Okay, so we can get the maximum area. 25 times 50 is gonna give us 1,250 square units. Okay, that is the maximum area. Okay, so this is actually how you go about these questions of maximization, optimization, and rate of change. Don't forget, it's very, very important that you know how to do this. The first step is for you to create an equation for something that you want to maximize. In this case, it was for area. So most of the time you'll get it that in your equation you have two variables, meaning you can't derivate, meaning you have to use another information given in order for you to be able to rewrite that equation in terms of one variable. After writing it in terms of one variable, derivate it and solve for the dimension that you want, and you can actually answer the question, get the maximum area and also the dimension if they need that. All right. Right, great stuff. Here's your interactive activity. Please kindly pause the video and try to answer this question. Drop your answers in the comment section and I'll just respond from there. I'd like you to answer A and C, because with B you won't be able to show it on the comment, right? So just give me your answer for A and for C and I'll just respond from there. All right. Okay, let's now look at the last section of this topic, application of calculus. Let's look at some of the theories on calculus of motion, right? So you need to understand what your displacement and what's your velocity and what's your acceleration, how are they related in terms of calculus. So For example, S of t represent an equation of motion, right? So it can represent your height, it can represent your distance, it can represent your displacement. Sometimes they can use m of t, sometimes they can just use anything, any letter, right? So showing you the displacement at time t, or rather the distance at time t, or rather the height at time t. So what actually happens is that when you derivate your displacement, right, or your distance, when you derivate it, s of t, when we derivate this, the derivative, or rather let me just write it by symbol s of t like that. So the derivative of your distance, height, or displacement will actually be equals to your speed, right, or rather your velocity. Okay, so and why is that the case? Why, when we derivate distance or displacement, we'll get a speed or velocity? Is because when we derivate, actually we're actually finding the gradient, right? So we know that the first derivative is the same as the what? As the gradient. Okay, so if we want s of t, the gradient of s of t between 1 and 2, right, we're gonna say s of 2 minus s of 1 all divided by 2 minus 1, which is our gradient, and this is actually the same as the first derivative. Okay, so the gradient of that is the same as the speed or velocity. Hence we are saying when you derivate your distance or displacement, you get your what? Your speed or velocity. Okay, so when you further derivate your velocity or speed, now you get the second derivative of this, you'll get your what? You'll get your acceleration, okay, as denoted here. So s of t will represent height, distance, or displacement. The first derivative of that displacement, when you derivate the rate of change in displacement, you know that is the same as what? As velocity. So represented by the first derivative. So to represent the velocity or speed, then when we derivate that velocity or speed, the rate of change in velocity is what? Is acceleration. Rate of change in speed is acceleration. Then when you derivate your velocity, you get your what? Your acceleration. Okay, let's just quickly look and take a look at an example in order to help you to conceptualize this. Particle moving along a horizontal line, right? The particle's position function is given by s of t is equals to 2t exponent 3 minus 3t squared minus 12t plus 8 for all values of t greater or equals to 0 measured in seconds. All right, so they gave you the function for the position, or rather for the distance that this particle is moving, right? So A, it says find the velocity function of the particle, right? They want you to get the velocity function of the particle. Remember, you are given the position, or rather the displacement, right? We can say the displacement or distance of the particle, the equation of that. Now they want you to get the function, or rather the equation of the what? Of the velocity in your A. How do we get the velocity? We have learned that velocity is actually the rate of change in position, or rather displacement, meaning that to get velocity we simply derivate our displacement, and we say we are getting the rate of change, right? Then we get our velocity. How do we derivate that? 2 times 3 is going to be 6. T exponent 3 minus 1 is going to be t squared. Minus 3 times 2 is going to be minus 6. On the exponent we subtract 1, we're going to be left with t. 1 times minus 12 is minus 12. T exponent 1 minus 1 is going to give us what? It's going to give us t exponent 0, and t exponent 0 is the same as 1. So it's going to be minus 12 times 1. It remains minus 12. What's the derivative of 8? It's going to be 0. So then this will be our what? This will be our velocity function. So the first derivative of the position or displacement, don't forget, it gives us the what? The velocity. Because when we get a derivative, it's like we're getting the gradient. And when we're getting the gradient, it's like we're getting the rate of change in that position, which is the same as velocity. Okay, let's quickly go to B. So B, they want you to also find the acceleration function of the particle. Now you have the velocity function. How do we get the acceleration function? We derivate again the velocity function or equation in order for us to get the what? The acceleration function. And why is that the case? Because we know acceleration is the rate of change in velocity, and the rate of change is actually the derivative of the velocity. That's how we get the rate of change, right? So now we are going to derivate again our velocity in order to get what? Acceleration. So when we derivate this again, it's going to be 6 times 2, it's going to be 12. T, 2 minus 1 is going to be t. Minus 6 times 1 is going to be minus 6. T exponent 1 minus 1 is going to be t exponent 0, which is the same as 1, right? So minus 6 times 1 it's minus 6. So that one will be our what? Our acceleration function. Let's go to C. C says, what is the speed of the particle at t equals to 5 seconds, right? So now they want you to get the speed, or rather velocity, of the particle at t equals to 5 seconds. We already have the velocity function. So what we actually go and do is we are going to our velocity or speed function and replace t by what? By 5 in order to calculate that velocity or speed when t is equals to 5. So it's going to be 6 into 5 squared minus 6 into 5 minus what? Minus 12. Then we can just quickly punch the calculator to get what? The answer of that. So on my calculator, I'm getting 108, right? So it's gonna be 108. This was measured in what? In t, which is seconds. And I just want to see if there is a unit that was given. It's only second, so it's gonna be unit per second. All right, so it's 108 unit per second. So that will be the speed of this particle. All right, let's just look at a different example in order to help you conceptualize this. Displacement in meters of a car t seconds after going through a traffic light is given by the formula S of t is equals to 10t minus 0.5 t squared. So this is a equation for the what? For the displacement of a car after passing through traffic lights, right? So A, they want you to calculate the car's initial velocity. Okay, so you are given displacement equation. How can you get the initial velocity? So if we are given displacement, to get velocity equation, we derivate our displacement, because when you are derivating, actually you are actually getting the rate of change of that thing. In this case, you will be getting the rate of change in displacement, which is actually our what? Our velocity or speed. So what we'll do first is we are going to derivate the equation. So it's gonna be 10, right, minus 0.5 times 2 is gonna give us 1, right? Is it 1? 0.5 times 2. Yes, it's gonna be 1. Then t 2 minus 1 is gonna give us what? It's gonna give us exponent 1. So that is our velocity equation, right? So from that velocity equation, we can get the initial speed, right? So the initial speed obviously is when t is equals to 0, right? So it would be 10 minus 0, then it's going to be 10 meter per what? Per second. So that is our initial speed. Let's go to B. Okay, so B wants you to get the car's maximum displacement. What is the car's maximum displacement? You are just given a displacement formula here, right? And they want the car's maximum what? Displacement. Okay, so what do we do in this case? So we need to what? We need to maximize the what? The displacement. Don't forget, we want the car's maximum displacement, and we need to go and use the ideas of maximizing the displacement. What's the first step in maximizing the displacement, or rather maximizing something? We have to write down the equation of that thing. So in this case, we'll first write down the equation of the displacement, right? Then what do we do after that? we get the derivative of that thing. So we first make sure that the variables are the same. In this case, it's much better because the variables are the same. Then we can get the first derivative of that thing, right? We have already calculated it, which is 10 minus what? Minus t. We equate our first derivative to 0 and solve for the variable. So we'll solve for t. T will be equals to 10. So it's measured in seconds, is equals to 10 seconds. So when t is equals to 10 seconds, our displacement will be maximum. So that's the idea. But we need to get the car's maximum displacement. We'll go back to our equation. We substitute 10, which will enable that our displacement is maximum. So on our original equation, we go back and substitute 10 and solve for the maximum displacement. Okay. So when we use the calculator, it will give us 50, and the displacement is measured in what? In meters. So the maximum displacement of the car will be what? Will be 50 meters. Let's quickly go to C and conclude our lesson. What is the car's acceleration after 10 seconds? So now they want the car's acceleration. You are given the equation of a displacement, where we can get the equation of a velocity, which we have already done by derivating our displacement. Then we know acceleration is the rate of change in velocity, meaning that we need to get the second derivative of the what? Of the velocity, so that we can get the rate of change in that velocity. So we derivate the velocity again. So the equation for velocity is 10 minus t. When we derivate the velocity, is going to be what? Let's check. So 10, the derivative of 10 is 0. The derivative of minus t is going to be minus 1 exponent t exponent 0. This will be minus 1, right? Meters per second squared, because it's acceleration. So that is the car's acceleration after 10 seconds. It's just going to be constant. It won't change. It will remain minus 1 meters per second squared, because it's constant, right? We can't go on t and replace by 10, because when we derivate, even if you come here and you replace by 10, you'll get that it will still be minus 1 meters per second squared. Okay, otherwise, great off. That's all for me. Thank you very much for joining this lesson. I hope you learned something on application of calculus, optimization, and rate of change.